Here I am. I'm in the middle of the screen today. I forgot to draw enough room on the side. We're going to be talking about charge transfer in this video. Now, in the previous video, I introduced charge theory, the idea that objects can be positively charged, negatively charged, or uncharged. Well, going into this video, we're going to be talking about how they end up positive or negative or uncharged in the first place. And to start that off, I'm going to talk about insulators and conductors, which are things that can accept charges, but do different things once those charges get on there. I want to emphasize first that when I talk about insulators, there's a common misconception that students assume insulators cannot accept charge at all. They think about insulators as being like immune to everything electrical. That's not accurate. You can put charge onto insulators. What's important about it is if I brought some kind of really positively charged object towards an insulator and I tried to transfer positive charges onto that insulator, all of it would stay in the exact same spot. It wouldn't move around. An example of that is a balloon. If you get a balloon and you rub it against your hair, you can notice right away that only one side of it is charged. It doesn't charge the opposite side. When you put it near your head, the side that you rubbed moves, the hair goes towards it. But if you flip it around, there's really nothing going on there. That's because it is an insulator. It will accept the charge, but it won't spread the charge across the whole thing. Another example of this would be like a slide at a playground. You guys have had that experience before where you go down the slide, you get super shocked as you go down the slide. And if you put your hand near it, you can feel all the little hairs on your arm attracting towards the charge that's on the surface. But if you put your hand under or on the side or basically anywhere else on the same slide, it doesn't do anything because the charge didn't move across that big plastic object. It just stayed on the surface. So we did transfer charge. We did put it on there, but it just didn't move. If I compare that to a conductor, if you try to put some charge onto it, it accepts the charge, but then it spreads the charge as evenly as it can all over the object. And so that would be anything that's made out of metal or whatever. And that's where the idea that conductors are better with electricity than insulators come from. Because if I put charge onto one side of a wire, that charge will work its way all the way over to the other side of the wire. Which if I'm trying to send some kind of electrical signal or I'm trying to send power is useful. Whereas with an insulator, I could put a ton of charge on one side. It just would never make it to the other side. So it's not useful for a lot of electrical applications. It still can accept charge, but it just can't move it through there. Okay, so that's insulators and conductors. Now with insulators and conductors, there's a couple different ways that we can charge them up. The first way that I can do it is by friction. So imagine that I have two objects that are initially uncharged. So you can tell that they're uncharged because you see that I have a combination of positive and negative charges, and they have an equal number of those. In this case, they have two of each. So each one of those bars that I'm rubbing up against each other has a net charge of 0, meaning that they're currently uncharged. But as I rub them up against each other, charge is going to start to transfer over. These negative charges might transfer over to the left-hand one, and who cares? Some of the positive ones might move over to the other side. So then at the end of the day, what I might end up with is, let me just erase this and we'll go to what it looks like at the end. And this is definitely a simplification. There's millions of these that are moving around. So we don't really end up with something that's pure negative and something that's pure positive, unless we're just doing a simplification here. But you can see that now that I've rubbed them up against each other, one of them's ended up negative and one of them's ended up positive. Now, what it turns out works best if you're trying to generate electricity by friction and create charge there, is to use insulators, because then when you're rubbing them up against each other, the charge will transfer and then it won't really go anywhere else. You can do it with conductors as well, but it kind of like works out that as you're charging it, then the charge conducts through your body, and at the end, it seems like you haven't accomplished anything. So that is charge transfer by friction. And interestingly, we don't really know how this works. Like the idea of somehow just like rubbing off electrons and they transfer like paint would, or like if you had marker on your hand, you rubbed it, some of the marker would end up on your other hand. That doesn't really work. We don't really know why some of the charge seems to prefer to move from the balloon to the hair, but not from the hair to the balloon. There's a lot of questions there about why that happens. It's called the triboelectric effect. And even more interesting to me, as far as I can tell, nobody really cares that we don't know why this happens. It gets kind of discussed a little bit, and then most people are just like, it happens. Who cares? So that's the first option, by friction. The next way to transfer charge is by conduction. Conduction would work if you started with one object that is charged and one object that is maybe uncharged. And when we touch those two objects together, they're going to try to equal their charge density or equalize their charge density. So since one of my objects is over positive and the other one is neutral, some of my positives are going to move to this new object. And at the end, my object that was originally uncharged is now positive, but my other object is still positive too. You can't transfer all of the charge by conduction. You really just kind of like equal it out. If they happen to be equal sized objects, equal amounts of charge go between those two things. But if one of the objects is much bigger, then the charge only separates based off of density, not based off of like equal numbers in each thing. And so um, that's why if you are electrically charged and you touch the earth, it almost always discharges all of it because the earth is so massive that whatever charge you carry with you from like being in the car or like walking with like those like those like nylon pants that always generate a ton of charge from when I was a kid. If you do those things, once you touch the ground somewhere you can ground out, all of the charge is basically going to go out of your body into the massive body of the Earth, and then you're uncharged or more or less uncharged again. So that is by conduction. The last one is the most complicated one, which is the idea of charging by induction. So in charging by induction, the first thing is I bring a positive object or a negative object, that part doesn't matter, but I bring a charged object near an object that's initially uncharged. So in this initially uncharged object, the charges are evenly distributed. There's positives in some areas, there's negatives in other areas. But when I bring this charged object nearby, there's going to start being an induction of charge separation. The charges are going to start migrating through the object based on their attraction or repulsion effects from the charged object. Now, this does mostly require conductors to charge by induction because you have to have that ability to move some charges around. So I'm going to move those charges around real fast. I had two positives and two negatives, and the negatives are going to kind of attract towards this left-hand side, and the positives are going to get pushed away because they're being repelled by the other positive charges. And so at the if I haven't touched them, by the way, this is just nearby. I've just like separated these charges, and then if I brought that positively charged thing away, the charges would move right back in, and it'd go back into being like uncharged. I mean, I apologize for being weird about this. It is uncharged right now. It's just got a relatively positive charge on one side and a relatively negative charge on the other side. So I haven't actually caused a change in charge yet. What I would do if I wanted to create these charged objects is I could break them right now. So if I broke them in half suddenly, while this positive object was still nearby, and now it's like two separate objects. Well, now the negatives are stuck on that end, and the positives are stuck on the other end. And I've now created a charge separation, and I've created two charged objects where originally I had an uncharged object. So these are the three different methods of charge transfer, but all of them demonstrate one very important principle, both for electrostatics and for our unit going forward, and that is the principle of conservation of charge. The idea that charge cannot be created or destroyed. All that happens is that it moves around. In the example of charging by friction, the charges directly transferred between the two surfaces. As they were rubbing, some negatives jumped to one side, some positives jumped to the other side, and we ended up with charged object at the end. We didn't create charges when we did that. We just moved them between the objects. A similar thing happens when we charge by conduction. I move that one object in, charges jump to the new object, and this is now charged, but because of conservation of charge, my first object is now less charged than it was. And however many charges my originally uncharged object gained is how many my charge object just lost. When I charge by induction, a lot of the times students get the impression that somehow charge was created because nothing touched here. But I didn't create charge here. The charges already existed in the uncharged object. They got separated by the induced effects of bringing that positive object nearby. And then when I separated the two objects, or separated the one object into two, now they have a negative and a positive based on the negatives and positives that they started with. So at no point was charge created, it was just moved around in the same way that we've seen energy move around or we've seen momentum move around. So conservation of charge is a very similar idea that's going to come up when we talk about electrostatics, and then again will be very important as we start talking about circuits. So that's what you need to know about charge transfer. Thanks for watching.